Thanks for coming, and today let's talk about running your Linux workloads faster, leveraging all the improvements we've made for the Azure platform. Before we dive into things, I'm Josh Polson. I'm a program manager from the Linux Systems Group, part of the Core Operating Systems Group. We've been delivering Linux drivers and other things for over a decade, and I'd like to thank that team for all the hard work they've done to make things run well in Hyper-V and in Azure. Today, we're going to talk about Linux on Azure, of course, and we're going to talk about some fundamental enhancements for the Azure platform that have been done for Linux, and well, of course, ended up with a summary. We're going to talk a little bit about networking, HPC, GPUs, and storage. I'm going to do a little demo of each of those things. For this session, I'd love to hear lots of questions. So there's a couple of microphones set up here. Please come up and ask a question anytime, and we'll get into it. If it's a deep question, I might redirect you to the booth, and we'll talk about it later. So, Microsoft loves Linux. And the reason that Satya Nadella put this slide up many years ago now was because we wanted to emphasize that we really got that our customers were running Linux. They wanted to move Linux workloads into Hyper-V and onto Azure. And we want to make sure, I'm not sure why this is clicking ahead. We want to make sure that everyone understands that we get it. You're going to run Linux workloads. You love them. We're going to make them run well in Hyper-V and Azure. So let's talk a little bit about the history of Linux in Azure. It's been there since the beginning. Since preview of Azure, there have been a couple of different distros that have been available. And since underneath the hood, Azure uses Hyper-V virtualization, you'll notice that the Hyper-V device drivers that were produced by my team have been upstream for over a decade, and have been filtering their way through the Linux kernel and into all the various distros. Each Linux distribution that's endorsed on Azure takes these drivers and backports them to the kernels that they're using and integrates them in such a way that when they make marketplace images, they just work right out of the box. Almost all the hardware capabilities are endorsed, and I'll talk about some of the tweaks because of things that came later. But otherwise, you can run almost any Linux distro in Azure and get something out of it, and the endorsed distros have done a great deal more work beyond that. So this is, of course, a little bit of an eye chart, but nonetheless, all these are the endorsed distributions that run on Azure. Red Hat's been there since 6.7. It's been a very tight relationship. CentOS also has been there for quite some time. Ubuntu and SUSE with SUSE Linux Enterprise Server all had great support. This is going to drive me crazy. All right, Oracle Linux is there. Debian has been there for quite some time. It goes all the way back to Debian 7. Of course, that's end of life. But Debian 10 and beyond are definitely well supported. CoreOS is there too because they also pick up the latest upstream kernels and integrate it into their work. There's more information at the link at the bottom there. You can talk, or you can just search for Azure endorsed Linux, and you can find all sorts of information. Each of the distros has done work on their kernels. For example, while the Red Hat kernel may give you a version that seems like it's old, it's not old. Red Hat does a lot of work to backport all of the things, all of the Hyper-V things, all of the other things into their kernel. So even though it says 3.10, all the latest enhancements from well beyond that have been integrated and are supported by Red Hat. And Red Hat makes one kernel for everything, so they don't have any specialized kernels or stuff like that. On the Ubuntu side is kind of the opposite, where they have this hardware enablement stream of kernels, and there's a Linux Azure version of that that tracks along with it. So on 18.04 right now, the hardware enablement kernel is 5.0, and so is the Linux Azure kernel. They continue to backport lots of stuff from upstream and include it. Ubuntu also picks up some stuff that hasn't even been accepted upstream yet for bug fixes and stuff like that. Red Hat also does that. But for the most part, got to go upstream first. CentOS kernels are based on the Red Hat kernels of the same vintage. SLES has their own Azure-tuned kernel. It's based on the same 4.12 they use for their generic kernel. Again, all the stuff gets backported and updated quarterly. Oracle's UEK is based on the 4.14 upstream long-term support kernel. They have also backported a great deal of support, especially for accelerated networking and PCI pass-through. Debian 10, of course, Debian 9 with the backports kernel, which has the same kernel as Debian 10, also supports the latest. And they have cloud versions of these same kernels that you can use. CentOS and Debian both have kind of these cloud versions of their kernels that you can also use on Azure. Now, for those of you that want to do very, very old versions of CentOS or RHEL, but you want the latest drivers and updates, there is a download from downloads.microsoft.com called Linux Integration Services. All it is a number of RPMs to pull in the latest Hyper-V device drivers and fixes. This is a way to get features into older kernels. Red Hat and CentOS don't take features into older releases. They only take bug fixes, so this is one of the ways to get ahead. All of LIS is tracked out on GitHub. It's been there for many, many years. It's all open source. It's all based on upstream patches to the kernel or things that are on their way upstream. And you can actually go to that LIS link there and grab just the tarball for the 64-bit and install it. Just remember that if you install a third-party driver like LIS or even GPU drivers or things like that, Red Hat won't explicitly support you. So that's a consideration to think of. But for the most part, if you can recreate it with LIS installed, you can probably recreate it without LIS installed, and Red Hat will certainly support you. There's some special things about LIS. For example, accelerated networking for CentOS 6 and RHEL 6 is possible with LIS because it introduces the PCI pass-through feature to those older versions of RHEL and CentOS. This is definitely not a supported configuration by Red Hat, but it is useful. If you're making your own image, and there's other sessions about migrating and lift and shift and stuff like that, you do need some specific Hyper-V device drivers in your kernel, and these are the 4 that I would call out. There's also some links here to do your own work if you want to. Let's talk a little bit more about networking. I already hinted at accelerated networking. At its very base, the NetVSC device driver looks like any other Ethernet driver, but it also has all the interesting capabilities of Hyper-V embedded within it. So you can take use of all these offloads that you can normally do with a Windows host. If you're trying to get the maximum throughput, then I recommend using as many connections and threads as you need. A single thread will experience some latency going through the host and out to the network that you may not enjoy so much, but you can still get 8 gigabits per second out of it and up to 11 gigabits per second out of a single thread. No other drivers are required on your Linux VM to make use of NetVSC, so this is definitely the standard path for getting things. There's a couple more links here about how to do benchmarking and a little bit more about network throughput. Each VM size in Azure has a limit that they have for how much network throughput you can do. Anything you push more than that limit will just drop in your packets on the floor. And that's to be fair to all the other VMs and other people that are running in Azure. So be aware of that. We don't do explicit throttling, we just drop your packets. Now, accelerated networking is based on single root I/O virtualization. It lets you talk directly from the VM to the network card without having to go through the host at all. This is a separate path. Now, because it uses PCI pass-through to expose this interface to the guest, you'll need to actually have a driver in your guest to actually make use of it. It's called a virtual function driver, a VF. So the Mellanox drivers are needed in Azure all the way from ConnectX-3 up through ConnectX-4. So you'll need to have that VF in there. And all of these distros have incorporated PCI pass-through and have incorporated the Mellanox VF driver, and it'll work out of the box. So I mentioned Red Hat there with a little bit of a tongue-in-cheek because, of course, you have to use LIS for that one. But for 7.3 plus, you can do it. 7.3 itself also requires LIS because we have an update to both the Hyper-V device drivers and the Mellanox device drivers to do that. But 7.4, 7.5, all the way up, that all works. 8 works. Obviously, the Azure tuned kernels work for Ubuntu and SUSE, and UEK5 on Oracle. Most of the time, if you're running Oracle Linux, you're also running Oracle database. You have to run a UEK to get support. So UEK5 is the place where you get that support in accelerated networking. That's Oracle 7.5 plus. If you use the Red Hat compatible kernel with Oracle Linux, of course, it's the same story as Red Hat. There's an asterisk here for Debian 9 because you have to use the backports kernel to get the required support. There are some other interesting networking technologies out there. Data plane development kit is a way to do more of your packet processing in user space instead of in the kernel, and we certainly support that. We do recommend some specific long-term support versions. 18.11 was the first one, the first long-term support version that supported DPDK in Azure. And 19.11, which is coming out this month, and the 11 is November, and that'll have multi-process support, so you have multiple processes cranking through packets. This is the way to go. Many distros also need you to download or install a new version of libRDMA CM, otherwise known as RDMA core, which contains the user space drivers for Mellanox. Version 17 is the minimum required. Version 23 I'd recommend at this point. The other way that people get this is they install Mellanox OFED. Mellanox OFED installs new Mellanox drivers in the kernel, but also installs new user space driver. Both the InfiniBand verbs and RDMA core get updated when you install OFED. I mentioned Express Data Path here as another protocol that people enjoy for packet processing. Nothing special you need to do here except you need to have the latest versions of the distros. There were a couple of bugs we had to fix. And we're still working upstream on explicit support of NetVSC for this. But enough talk. Let's actually try something. So I have a couple of F72 VMs here. On the right here, I'm going to start a receiver. And on the left, I'm going to start a sender. And what's going on here is that we're using a tool called NTTTCP, which was a port of a Windows tool that does network bandwidth testing. But you could use iPerf3 or iPerf or other things like that too. But the reason we liked NTTTCP is because we can do interoperability with Windows and because it's multi-threaded and multi-connection by default. You can actually get this particular program off of GitHub. It's one of the ones that we ported and made available for free. It supports all sorts of mini options. I'm just doing it with default options here. And you'll notice that this F72 V2 here is doing 30 gigabits per second. I run this test for about 60 seconds. So what's going on under the hood here? This is an SRIOV-based connection. We're doing 60-some threads here. We could do more, we could do less, but in fact, you could actually get this kind of performance with just 8 threads. And the main reason for that is that it can crank pretty good here, and there's not a lot of CPU utilization. On the sender side, there's also a report. So I recommend NTTCP or iPerf3 in doing your own tests, cranking away, and looking at the limits that are available for your particular VM size and see how you're doing. So there is another tool called LagScope. And the Windows version of this tool is called Latte, but that's an overused term in open source land, so I didn't want to use that. So we renamed it to LagScope. And what it does is it measures latency. And if you want the best latency for an Ethernet connection in Azure, you want to use SRIOV as well. So it's cranking away here. It'll run for about 60 seconds. As you can expect, there is actually a LagScope GitHub as well, and you can go poke around and play around with it. This one uses CMake, all sorts of fun stuff. People don't necessarily care about reading the README, but nonetheless, this is the best latency that you're going to get in Azure, but for Ethernet. Infiniband is going to be another story. I'm just giving you a little bit of a preview here. All right, 60 seconds is a long time. That's what I get for talking fast. All right. Again, if you have any questions, please come up and give us some questions. Usually I get a question or two by now. All right. So, a minimum of 37 microseconds, an average of 67 microseconds. Pretty good. Not too bad, right? Let's go back to the presentation. All right, so that's basically the idea with networking. I recommend that you go try this with synthetic networking and stuff like that and see what you think. You can get really good throughput and latency with synthetic networking. It's just not going to be as good as SRIOV for the same number of connections. Let's move ahead to high-performance computing. There's a number of HPC SKUs that are available in Azure. There's 2 different kinds of InfiniBand available in Azure. And of course, we want to make sure we support Infiniband with the distros. So the original Infiniband that we offered years ago was based on a special RDMA driver called Network Direct. This was before we had SRIOV working. And there's many HPC images on both CentOS and SUSE that have these older drivers available. And it had a lot of limitations. It didn't support all the Infiniband verbs. It only supported Intel MPI. It's only, and then that worked with a lot of different applications, but nonetheless, it's much, much better to be replaced by SRIOV. The reason for that is that SRIOV lets you use any MPI library you want, Intel, Platform, OpenMPI. It's all working out of the box. In fact, I'll show HPCX in here in a minute. But of course, to use SRIOV, and the older SKUs will migrate to SRIOV over time. You need newer versions of the distros than the older ones. So RHEL 7.5 would actually work out of the box. Ubuntu Azure Tune kernel, the SUSE Azure Tune kernels also work out of the box. But most of the time, the HPC guys are recommending that you install the InfiniBand drivers from Mellanox, which is Mellanox OFED. And the reason for this is not only does it update the kernel driver and the user space drivers, which is this RDMA core and IBverb stuff, it also has lots of diagnostic tools that help you figure out what's going on in your network that aren't really there in the base distro. So let's do a quick look at that. So here, let me get the right one. So here I'm going to do a quick MPI run job on a node setup, a 2-node setup that we set up this last night, and see what kind of bandwidth we can see. So the card that backs this up is a separate card from the other one that does Ethernet networking, and it has 100 gigabits of bandwidth over the InfiniBand network. Pretty straightforward, right? Let's do the latency one instead. So you can see here that while we say that we can do less than 3 microsecond latency with this, I'm getting 1.5 microseconds of latency with smaller sizes of my messages. And as slowly as it goes up, it gets a little slower. 3 microsecond latency, gotta love it, right? You can't get that with Ethernet. All right, moving ahead. By the way, that was an HC44RS. That's the Intel-based one. There's also HB-based ones. They're AMD-based. HB is AMD-based. HBv2 is AMD's EPYC Rome. So let's talk a little bit about GPUs. I mentioned how PCI pass-through and DDA are used to project Mellanox NICs into the guest. The GPU SKUs can also project GPUs into the guest. NC versions, starting with just the regular NC version 1, started with those K80s, and an NV series is based on Maxwell's. So all of the versions require PCI pass-through to work. On the NC and ND side, you can use the regular CUDA drivers that come from the NVIDIA development repository. On the NV side, for streaming and visualization, you have to use a special grid driver, which requires lots of licensing, so we just can't just put it out for everything. But there is a repository and instructions for installing it from our repository. But even better, there's an extension for installing the GPU driver, because this is a third-party driver. It's not going to be carried just by default in the distros. You can either use the extension, which will go through and set up DKMS and all that other nice stuff and reboot your VM a couple times to get everything all set up, or you can follow the manual setup instructions that I've included here. Everyone's really excited about installing GPU drivers, I know, but nonetheless, because they're a third-party driver and because they're a binary-only driver and at its core, it's a little bit hard for the distros to carry it with and can claim supportability. So let's take a look at what that looks like. So imagine, if you will, that I went through the portal and I already went through the graphics driver extension for Linux and installed all the graphics drivers on this node. This happens to be a CUDA-based node. And this demo is going to be a little bit different in the sense that what I'm going to do here is I'm going to watch NVIDIA SMI, and I'm going to have it set at a 1/10 of a second interval. And the reason for that is because I'm going to do one of the samples out of the NVIDIA toolkit, and it runs rather fast. So on the right, you don't see any processes making use of the GPU. And it was there for a second. Did you see it? All right. The demos that are in there are just a bit fast, but you can actually see that it did produce a Mandelbrot set. And yes, I am tunneling X11 from a node out on Azure to my local machine here with X410 on top of WSL2. Okay, too many buzzwords. All right. Nonetheless, there it is. You can see that it definitely created something, and it did it very quickly. All right. Thank you. I'm here all week. Let's talk a little bit more about storage. So, just like on the networking side, on the storage side, there are also a number of synthetic drivers. Actually, there's one. Store VSC, just like NetVSC. And all of the various offerings that you can get in Azure are available through that same driver. Standard HDD all the way up through UltraDisk. You can get more information about all the various disk types here. There's a FAQ there as well. But for the most part, Store VSC has been supported for a very, very long time. You may remember back in 2016, we talked about premium storage, and everyone needed to backport the XIO drivers into their various distros. That's been around since 2016, so you can imagine your support is actually pretty good right now. Not so bad, right? Even UltraDisk, you're talking about 80,000 IOPS. Let's move ahead to storage optimized virtual machines. The new L80V2 instance type, and in fact, the whole LV2 size, projects storage into the guest not as SCSI devices, but instead as NVMe devices. And this is going to be the wave of the future. As you can imagine, L80V2 with 12 NVMe drives, 8 channels per drive, it ends up being an interesting challenge. In order to get all the right fixes for all these distros, actually fairly newer. So, for example, I mentioned RHEL 7.6 with an asterisk here. You actually need the very latest version of RHEL 7.6 to pick up an important fix there. RHEL 7.7 works out of the box. RHEL 8 works out of the box. Debian and Ubuntu are here. The only reason I'm not listing SUSE is that same bug that we fixed is still being fixed on the SUSE side. Once it's there, then you won't have any soft lockups and we can move forward, right? So, go ahead.
Is this for all disks or only locally attached?
So, the question was, is this for all disks or only for the locally attached? This is for the NVMe projected disks. On this particular VM size, because there's so many channels doing work, that we ran into some soft lockups that actually was a bug upstream that we had to get fixed there first. Did I answer your question?
I'm saying, are all disks projected as NVMe or only the locally attached ones?
Only the locally attached ones. So there's 12 locally attached NVMe drives that are sent to the L80. So those are the ones that are get projected as NV. Store VSC is still used for all the other storage that you're probably going to use to get your data onto those disks. All good? Yeah?
So we're running some automated testing where we're spinning up ephemeral VMs, in this case CentOS VMs in Azure, and we're using Ansible under the scenes to do that. But I'm seeing something where when we spin up a machine, regardless of the storage that I was using, seeing some initial latency with installing some Docker containers, wrapped with systemd. But after about 30 seconds, then I would see the performance that was sort of, advertised with just different storage levels. But for some reason, in the first 30 seconds, I would see some timeouts with systemd trying to pull Docker containers.
So if I can summarize your question a little bit, you're seeing some latency at first doing writes. So remember that all your storage, when you do writes, goes sent to 3 places, and it has to be finished in all 3 places before it's kind of marked done. So you can do some caching to help with that a little bit, but nonetheless, in order for all the redundancy to work, that's why you get latency at first, because it's establishing all 3 and sending it all 3.
But that is something you guys are aware of, like initially just starting out?
You can see some latency, certainly, on writes because of that. That's probably what the case is. We could probably dig into it more offline if you want. All good? All right. So I think people want to see this too, right? So now we're going to do some work with storage. On the storage side, on the right side here, I'm going to have, I have a watch command watching IO stat. I'm only watching it every half a second instead of every 1/10 of a second. Storage takes a little bit longer than GPUs do. And then on the left side here, I am going to run FIO. And this particular FIO is doing writes. So we're cranking along doing writes, and we are seeing nearly 3 million IOPS. We're using a 4K block size, and we have 80 jobs because we have 80 CPUs. Cranking along, not too bad, right? This one takes about 60 seconds as well, but why not just kill it? Everyone's seeing that. Okay, that's no fun. Let's try to do reads. Reads are much more fun. All right. So now, on reads, as you can see, we're doing nearly 4 million IOPS. So when you're thinking about the premium ultra disk, those kinds of things, and 80,000 IOPS, now we're talking millions of IOPS with 12 disks. All pretty good? All right. So I didn't mention that on the HPC side, you can also create virtual machine scale sets like I did using another tool here. But let's go back to the presentation. All right, so I expected a lot more questions. So, do you all believe now that Linux runs great in Azure and you can get great performance? If you have any questions, bring them. I listed about 12 different places to find documentation in this deck. This deck will be available on the tool soon after this presentation. So definitely go poke around for the documentation. Of course, you can use your favorite local search engine for Linux and Hyper-V or Linux and Azure, and you'll find a lot. And then I kind of got to dive into a number of enhanced capabilities and how they're enabled in Linux distributions. All right? Bring on the questions. All right, well, thanks, everyone. Appreciate your time.